for
chemistry.
Yeah, baby.
Welcome to Let's Get to the Marks. I'm going through AQA Chemistry A-Level Halogenoalkanes, sometimes known as haloalkanes. This is found on the physicsandmathstutor.com website. Brilliant website, loads of past papers and good provision materials. Let's get into the pack. CFCs were used as refrigerants and in aerosols. The scientists Rowland and Molina published research in 1974 to show that CFCs are responsible for the destruction of ozone molecules in the upper atmosphere. A few years later, other scientists discovered that the concentration of ozone in the upper atmosphere was decreasing. In 1987, there was an agreement by many countries to restrict the use of CFCs. The molecule CFC11 was commonly used as a refrigerant. Use IUPAC rules to name CFC11. Once again, pause the video, guys. Have a go at the question on a scrap bit of paper, then unpause the video and check your answer against the walkthrough. So we need to ask ourselves how many carbon atoms are in this molecule. There's only one, so it's going to be a methane molecule, single bonds. There's 3 chlorines, so we use the trichloro, and there's 1 fluorine atom. So fluoro, put them in alphabetical order. Chloro, C before F. So trichloro, i.e. 3 chlorines. Fluoro, just 1 fluorine. Methane. So the answer to this is trichlorofluoromethane, and that is the name of this molecule. Of course, if you had to number, you would do 111 trichloro, 1 fluoromethane. But because there's only 1 carbon atom, we don't need to number it because there's no choice for another carbon atom. Now, coming down to this question, a molecule of CFC11 breaks down in the upper atmosphere to form a chlorine free radical. Write the equation. So we just need to write out our trichlorofluoromethane, so CCl3F. Ultraviolet light breaks it down in the upper atmosphere, and you're just going to split 1 chlorine atom off, give it an unpaired electron, which we show with a dot, and we have an unpaired electron on the fluorine as well. However, you could put these unpaired electrons anywhere on the free radical, so it could be before the C at the start. I like to put them at the end. And that's your mark for that. So let's move on to the next question. A typical refrigerator contains 0.50 kilograms of CFC11 with an MR of 137.5. 1 molecule of CFC11 causes the destruction of approximately 100,000 molecules of ozone. Notice what I'm doing here is I'm highlighting the units that you come across in these questions. Whenever there's going to be a calculation, you need to work out what equation you want to use. And we've got mass, we've got MR. So I'm pretty sure we're going to be doing mass over MR times moles at some point. Now, it's saying for every CFC, you break down 100,000 ozone molecules. Use these data to estimate the number of molecules of ozone that can be destroyed by 0.5 kg of CFC11. Give your answer in standard form. We are also given Avogadro's constant, which means you're going to have to use that as well. So my first, even if you can't work out what you've got to do here, first thing to do is say, well, I've been given M and MR. Let's work out the moles of CFC. So I've got 0.50 kilograms. What do we need to do to that? So we times by 1,000, we get 500 grams of CFC divided by the MR of CFC, which is 137.5. And that's going to give us N, which we use for the number of moles. And the number of moles is going to be something like 3.63. We could round that to 3.64 if it's bigger, and it is, because on my calculator it's 3.636363. So I'm rounding it to 3.64. That's the moles of CFC. So you've at least scored a mark here working out the moles of CFC. Now we want to know how many molecules of CFC do we actually have. So how many molecules of CFC do we have? Well, we're going to do number of moles times L, which is Avogadro's constant, and we'll find out how many moles. So there's 6.022 times 10 to the 23 particles of CFC in 1 mole. So we go 3.64 times Avogadro's constant. I'm using L here, and we get 2.19 times 10 to the 24. Now, what I also need to take account of, that's the molecules of CFC, but the ratio of CFC to ozone that's broken down is 1 to 100,000. So I need to times that by 100,000. So timesing it by an extra 5 zeros, so I can just add an extra 5 on there. So 2.19 times 10 to the 29. And that is the number of molecules of ozone that will be broken down by 0.50 kilograms of CFC. Okay, moving on, state the benefit to life on Earth of ozone in the upper atmosphere. What is the ozone for in the upper atmosphere? It absorbs harmful ultraviolet radiation, which is going to reduce the amount of skin cancer, reduce the amount of harmful UV radiation reaching human beings on the Earth's surface, essentially. You can say blocks UV light if you like. Suggest one reason why the use of CFCs were not restricted several years after Rowland and Molina published their research. Obviously, maybe we could say more evidence was needed, still needed to be reviewed by peers. Industrially, CFCs were the only thing that could be used in fridges. People weren't ready to give up fridge use yet until they found an alternative chemical to replace the CFCs in fridges and in aerosol cans. There's loads of different answers there. CFC is a greenhouse gas. How can that contribute to global warming? So really, this is a 2-marker. And molecules that contribute to global warming are polar molecules. That means they have a delta positive atom and a delta negative atom. And CFCs obviously have fluorine and chlorine, which are electronegative, and carbon, which is slightly electropositive. Therefore, if you have a polar bond, it will vibrate, and it will absorb infrared radiation at a similar wavelength to the vibrations or oscillations of that polar bond. Non-polar bonds, by the way, like carbon-hydrogen bonds, don't really absorb infrared radiation because they're non-polar and they don't vibrate in the same way that polar molecules do. You need to know that, so make sure you got that down for 2 marks because that comes up. Okay, moving on, we got some multiple choice questions here. That was the end of question 1. Let's get into question 2. Which compound is not formed by reacting 3-bromor 3-methohexane with warm ethanolic potassium hydroxide? This is where you've got to know your mechanisms for organic chemistry. Okay, I'm going to start by drawing out the reactant molecule 3-bromor 3-methohexane. So drawing that out there, 6 carbons. I can't be bothered to add all the hydrogens on, so I'm just going to leave open bonds. Just imagine there's hydrogen atoms there. Use your imagination. And I'm going to stick a bromine there and a methyl group on the 3rd carbon. Now, if it wasn't ethanolic potassium hydroxide and we just had like sodium hydroxide or potassium hydroxide ions, we get nucleophilic substitution. And I'm going to show you that here. This hydroxide would donate its pair of electrons to the carbon, and then the bromine there would snap off and you would have an alcohol formed. And you get that with nucleophilic substitution of halogenoalkanes with hydroxides. But that's not what happens here. This is the ethanolic potassium hydroxide. And with this one, we get the elimination mechanism. So we're going to get a double bond forming. And it's because, for whatever reason, when it's ethanolic, the hydroxide ions, instead of attacking the positive carbon, they attack one of the hydrogens on the carbon atom next to the bromine carbon atom. So it's going to attack that hydrogen, which is going to snap off to form a water molecule, and it's going to donate its pair of electrons to the carbon-carbon bond next to the bromine carbon, forming a double bond. Of course, the carbon atom attached to the bromine can't have 5 bonds. So if we get a double bond forming there, then the bromine atom must leave. And therefore, you're going to end up with like 3-methyl, 3-hexene, because you get the double bond there. Look, I've just drawn it there. So it'd be 3-methyl, 3-hexene, because we'd have that water molecule would be removed and that bromine atom. So 3-methyl, 3-hexene. So D can definitely form, and that's not what the question was asking us. It was asking us what cannot be formed. So let's have a look at the next one. So I'm redrawing our 3-methyl, 3-bromo hexane to start with. Again, this time let's choose a different hydrogen atom, the other side of the bromine, carbon bromine, that could be attacked. Now, if that's attacked, the hydrogen could donate its pair of electrons there, and the bromine will snap off and be eliminated along with the hydrogen and the hydroxide ion. And this time we get 3-methohex2-ene, because obviously that's the double bonds on the 2nd carbon, and the methyl group would still be on the 3rd carbon. So C is a true molecule that can be formed from this reaction. So that's not our answer either. Put a cross through that too. Now let's look at the third and final answer that's not correct. So I'm redrawing 3-bromo 3-methohexane here. So should have just kept leaving it on there, but there we go. I'm a bit stupid like that. So let's whack on the methyl group is on the third carbon, not the second. Having a bit of trouble here with my old drawing. And then we want the bromine group on the third carbon too. Now with this one, something interesting happens. Instead of the hydroxide ion attacking the hydrogens either side of the bromine, it attacks one of the hydrogens on the methyl group. And this means the hydrogen on the methyl group snaps off and joins with the hydroxide ion to eliminate water, but donates its pair of electrons to the bond between the bromine carbon and the methyl group. So you get a double bond here at this point. So effectively, I'm circling this in a kind of orange color. This creates 1, 2, 3, 4, 5. This creates pentene as the longest chain. So we've got pent-1-ene as the longest chain. And then these two carbons at the start of the old hexane chain, they become an ethyl side group. So this becomes, and they're found on the second carbon atom of the pent-1-ene chain. So this becomes 2-ethyl pent-1-ene. Your double bond is there where the methyl group attaches to the old hexane molecule, but that has now changed its name to 2-ethyl pent-1-ene. So A is a true molecule that can form, and so again is not one of the correct answers. So the correct answer is 3-methyl hex-1-ene. So why can't 3-methyl hex-1-ene form? I hear you say. Why can 3-methyl hex-1-ene not be the correct answer? The hydroxide ion cannot attack the carbon at either end of the main hexane chain. Well, it can attack it, but that carbon, the hydrogen, is not going to form a double bond there and eliminate because your bromine's not leaving. So there's no need for that to happen. So, for instance, if the hydroxide group was to attack this hydrogen and somehow eliminate this hydrogen, there's no reason for the bromine atom to remove itself. It's completely stable there. So this molecule would not form 3-methohex-1-ene. It's only if the hydrogen either side of the bromine atom is attacked that the bromine would have to leave when a double bond forms next to it because there won't be room for it on the carbon atom. So it's not going to affect the bromine atom if the hydroxide atom attacks the first or last carbon there. Okay, moving on to question 3. I was waffling a bit there. The question below refers to the reaction of 1-bromopropane with a solution of potassium cyanide in aqueous ethanol. So this is a slightly different reaction that we've done. We've got 1-bromopropane and we've got potassium cyanide. So this is another mechanism you've got to know off by heart for your halogenoalkanes or your haloalkanes, whatever you like to call them. So let's draw out the reactant. We've got 1-bromopropane here. That means the bromine molecule is coming off the first carbon. And that's delta negative, more electronegative than the carbon atom. So the carbon atom is delta positive. And we just got a nice old nucleophilic substitution here, just like as if alcohol attacked under non-ethanolic conditions. So we draw our cyanide molecule. Remember, you need a lone pair and a negative sign somewhere on the CN. That's going to attack the carbon here. And that means that the carbon can only have 4 bonds. This would make 5 bonds. So the bromine has to go. So the pair of electrons from the bond will go to the bromine and that will come off. What will this do? This will extend the carbon chain. Using cyanide is a great way to extend the main chain in the number of carbon atoms. So look, we've gone up to 4 carbon atoms. So wouldn't this be butylamine? No, because amine, remember, is NH2. So that would be if you were using ammonia. You get nitrile when you use cyanide, but you would increase the length of the carbon chain. So this would be butan nitrile. Now notice you leave the E, that's really important. It will be butane nitrile. You don't say butan and drop the E, otherwise you get 2 N's together with the nitrile and the butan and it doesn't look right. So they want you to have the E still in there. Question 4, the question below refers to the reaction of 1-bromopropane with a solution of potassium cyanide in aqueous ethanol. So we've got the same reaction going on. The reactions of 1-bromopropane and 1-chloropropane propane, oh my days, I can't speak, with potassium cyanide and aqueous ethanol occur at different rates under the same conditions. Which row shows the compound that has a faster rate of reaction, or what's the correct reason for this? So what you're looking at here is you're looking at the bonds. So the only difference between one bromo and one chloropropane is the CCl bond and the CBr bond. They're both polar bonds, electronegative bromine and the electropositive carbon, electronegative chlorine and the electropositive carbon. Essentially, the carbon-bromine bond has a lower bond enthalpy. So the reason why one bromopropane will react faster is because it has a weaker bond. You can think of the argument that, but surely the chlorine is more electronegative, so it will make the carbon more positive, more open to attack, and all of that kind of stuff. That's not the reason. It's outweighed. Any other reasons are outweighed by the lower bond enthalpy of the carbon bromine bond, and the carbon iodine bond would be even weaker as well. Bromoethane reacts with potassium cyanide to form compound D. We just looked at that in one of the earlier multiple choices. Outline. Oh my gosh, I can't speak anymore. Gonna have to finish this video in a minute. Outline the mechanism for this. Oh my days, CH3. What am I doing? So what we want to do here is outline the mechanism for the formation of compound D. So we want to draw out the bromoethane molecule. So I've got the delta negative bromine because it's more electronegative than the carbon. It draws the pair of electrons towards it. This means the cyanide or nitrile is going to attack here at this delta positive carbon atom. I should draw the 3 bonds for the nitrogen, put the lone pair and the negative electron there, draw a nice curly arrow. Make sure it's not going to the bond. The curly arrow would be repelled by a bond. Make sure it's going to the atom. And then for the bromine, make sure you draw the curly arrow touching the bond and curling round to the bromine, so it's snapping off. And that's really going to get you 2 marks. There's no need for me to draw the product. So the product's right there. It's compound D. So I'm going to stop drawing that and wasting your time. That is your 2 marks, one for each of the curly arrows. The first curly arrow, you need to have the lone pair and the negative electron as well to get that first curly arrow. You don't actually need the delta positive and negative sign for the second curly arrow. And there we go. Give the IUPAC name of D. Well, let's bring the picture back up that we just made for the mechanism. And it is CH2. So, and we've got another carbon. There's 3 carbons. We've extended the carbon chain using cyanide. So it's now propan nitrile. However, you must include the E. So it's propane nitrile. Often with alkanes, like you will drop the E at the end of the propane. You don't here. You maintain it. Otherwise, you get this situation where I'd write propanitrile with 2 N's together, and it just looks ugly. So they're not going to accept that. They want you to have the E separating these 2 N's here. Okay, so make sure you don't make that mistake. Simple spelling mistake that could cost you a mark. So the IUPAC name is propane nitrile. Okay, let's zing down. I think we've got one more question to go for me to finish up this pack. C, calculate the percentage atom economy for the formation of D in this reaction. Give your answer to the appropriate number of sig fig. Sig fig. Right, so what you've got to do is useful reactants, which is the propane nitrile, over the total, useful products over the total products. So yeah, I'm going to do propane nitrile over propane nitrile plus KBr, essentially. These are the products. D is the one we're looking for the atom economy for. If we were looking at it for KBr, we'd do KBr over D and KBr added together. But we're not doing that. So we're doing useful product D over the total product. So we're going to do CH3, CH2, Cn divided by CH3, CH2, Cn plus KBr. Essentially, that's all you've got to do. Add up their atomic numbers, their mass numbers, sorry, not atomic numbers, got them all over the place. So 15 for CH3, because you've got 12 and 3, 14 for CH2, 12 and 2, 26 for nitrile for 12 and 14 added together. And then for potassium is 39, bromine is like 80, so it's like 119. So the total amount of product is 174. D adds up to 55, so we want to kind of do 55 over 174, and then we need to turn it into a percentage by timesing by 100. So 55 divided by 174 times 100, smash that in the calculator, and we get 31.609. Remember, 3 significant figures at A level, you must do 3 sig. They love the free SF. So you've got to do that, or 2DP. But if they say significant figures, you've got to do it to 3. So we want to go 31.6 as there's a 0 there. If it was greater than 5, if it was 31.66, we would turn it to 31.7. But as it's 31.60, we keep it at 31.6. Boom! Let's move on to the next question. Question 6. Which compound can react with ammonia to form propylamine? Okay, the clue's kind of in the name of the pack, right? It's kind of in the name of the pack. It's haloalkanes, halogenoalkanes. So the answer is not going to be an alcohol for this question. It's going to be the halogenoalkane, but that's kind of cheating if we do that, because you're not going to get that clue in your exam. So anyway, let's write out the reaction of ammonia with that bromopropane, which is C, just to show you that you should know this. This is the reaction that you get when ammonia attacks a halogenoalkane. You get an amine, and it's by what we got here. We got the delta negative. It's all about the delta positive and the delta negative, isn't it? So we got the delta positive carbon atom here, and we got the delta negative bromine here. And essentially what happens is we have our molecule of ammonia with its lone pair on the nitrogen. Remember, it's group 5. 3 of the electrons are bonded. It's got 2 spare electrons, the nitrogen. So it donates that lone pair to the carbon, which means the bromine's got to bugger off, right? Now, you might say to yourself, but doesn't that leave us with an NH3 group attached? It does. We get this intermediate now. So check the second part of the mechanism I'm drawing down here. I'm redrawing it out. This time the bromine is buggered off. It's been eliminated, possibly to react with whatever came with the ammonia or with the hydrogen atom that's going to come off now. Now, nitrogen doesn't like having 4 bonds. It's unstable. We call it a nitronium ion. It's got the little positive on the nitrogen. Whenever you see 4 bonds around a nitrogen, whack a plus onto it. What happens now is another ammonia molecule that's floating about comes and attacks one of the hydrogens so that it can form an ammonium ion, and that hydrogen donates its pair of electrons to stabilize the positive carbon. They go and join that positive carbon and stabilize that, and a pair of electrons donated from ammonia to that. So that now we end up with just an NH2 hanging off the end. And yes, that nitrogen has a lone pair, so we can have further reactions going on with that lone pair. That can go and attack another halogenoalkane to do further substitutions, but we're not going to worry about that. The answer for this is therefore C. Yeah, it can form propylamine. Okay, that's the end of the video. Don't forget, sharing's caring. Hit the like, subscribe, punch up the bell. Yeah, whatever. We got exams coming, people. Don't forget, it's time to work. Let's get to the marks.
I've had training.
The training is nothing. The will is everything.
The will to act. Yield.
You're still here? It's over.